Everyone, so in this video we're going to be starting on page 2 where we left off yesterday. And just to review, on page 2 we talked about our 3 methods of solving for an intersection point. Solving by graphing, where we can just find the point where they intersect exactly. Solving by substitution, where I isolate an easy variable, take that equal stuff and plug it into the other equation for that variable. Or elimination, where I'm trying to manipulate the equation so that when I add them, one of the variables, completely cancels out. 3 methods of solving. Now, what we're going to get into today is how we can solve a system of linear and quadratic equations strictly by graphing today. So maybe last part of class today or maybe beginning of class tomorrow, we'll start getting into how to algebraically solve these, but we're just going to start with the graphing side. We briefly talked about this yesterday, but I want to turn to page 3 and talk about it again. There are 3 possible cases we can have for solutions for a quadratic. We can have one real solution, where our graph of the line hits the quadratic in exactly one spot. We say here that the line is tangent to the quadratic or to the parabola. When it's tangent to something, it touches in only one spot. So maybe a term that you heard before in geometry where you have something tangent to something else, 2 shapes that are tangent to each other, they only touch in one place, where a secant would be touching in 2 places. So one real solution is a possibility. 2 real solutions is also a possibility. This line is hitting this parabola in 2 different spots. Now, our last scenario is when our line doesn't touch the quadratic at all. You might just say no solution, but from everything that we've done so far with the quadratic formula and how, it cannot touch the x-axis but actually have algebraic solutions, we need to specify that if they don't intersect, they have no real solutions. So, might have complex or imaginary solutions, when solved algebraically. So that's why we have to specify no real solutions, because when we solve algebraically, it might have complex solutions. Just like when we were solving quadratics for their x-intercepts, it's like, hey, it's just straight up not touching the x-axis, but using the quadratic formula, we still found that that had imaginary roots. So, folks, we are going to be brushing up on graphing lines, which will help us with the linear programming aspect of the final, and also a throwback to the last unit, if maybe that didn't go so well, with graphing quadratics by hand. So go ahead and flip back to page 2, and we're going to go ahead and start with example 1. Label number 1. And label number 2. So I'm going to label this one. Now, before we do anything, we're going to look at those equations and identify what type of functions they are. So as I look at that first equation, what is that? What form is it in? It's a quadratic in standard form. So I'm going to put Q for quadratic. Then, looking at my next equation, what's that? Y equals mx plus b. That is a line in slope-intercept form. So we have a quadratic and we have a line. let's go ahead and start by graphing the line since it's, just a little bit easier than the quadratic. So this line, y equals, oh my gosh, mx plus b, has a y-intercept of -6. So we're going to go down to -6 on our y-axis. And then our slope is 5. So up 5, 1, 2, 3, 4, 5, over 1. 1, 2, 3, 4, 5, over 1. 1, 2, 3, 4, 5, over 1. I better go buy some more popsicle sticks. How many of you guys still have your popsicle sticks from way back with linear programming? I'll go find some more. It shouldn't be an issue though with this, with the stuff we're doing today, because it will be extremely obvious where they are or are not intersecting, even without a ruler. So for right now, I don't know, your cell phones have a straight edge. Go ahead and best you can draw a line through those points. But also notice that I did go pretty much all the way up the graph as far as I could. The more exact points we have, the easier it will be to find where it does or does not intersect that quadratic. Also, make sure you label that line number 2. And now we're ready to graph the quadratic. Good news is we're actually going to be doing the same first couple of steps that we did on the homework quiz. Gotta find that axis of symmetry. Gotta find the vertex. So this is in standard form. So let's start with that lovely work we're supposed to show. The axis of symmetry is x equals -b, so -1, over 2 times the a value of 1. -b over 2a. So, what is our axis of symmetry? -1/2. I don't love it, but here we are. So that tells me the x coordinate of my vertex. Maybe I should be labeling these steps A and B, not to be confused with our 1 and 2 over there. So that leads us to the x part of our vertex. So -1/2. So because that's negative, do make sure that you're putting in parentheses around that value when you plug it in. So parentheses, -1 divided by 2, raised to the second power, arrow over to escape the exponent, plus -1 divided by 2, yuck, minus 2. And we get -2.25. Now, folks, since we're plotting this point, I would not do math enter, and turn this back into a fraction. I would go ahead and just leave it as a decimal. So -2.25. So let's go ahead and plot what we know so far. Our axis of symmetry is at -1/2. There's -1/2. And then our vertex is at -1/2 down 2 and a titch. So there's my vertex right there. Now, similar to how when we were trying to use graphing to find our x-intercepts, we don't know how big this quadratic's table is going to need to be in order to find the intersection point. We essentially have to keep getting points until it's obvious where it is or isn't intersecting that line. So I made a nice big old table, and I'm going to center it around the vertex. -1/2. -2.25. So I want to start going below the vertex and above the vertex, or rather left of the vertex and right of the vertex. Folks, if I look at that x value of -1/2, what is the closest integer to the left of it? It's this tick mark right here, -1. And then I can keep going, -2. Then if I wanted to go up or to the right of -1/2, the closest integer would be 0. And then 1. So we'll start with 5 points and see what that does for us as far as finding the intersection point. So lucky us, we already typed that sequence in on our calculator to find it for -1/2. So I'm going to hit second enter to copy paste, and I'm just going to delete the divided by 1 to turn that into the -2 I need for the first point. How sneaky of me. Sweet, that gives me 0. But I don't jump for joy like I did in the last unit because I'm not trying to find the x-intercepts here. Instead, we're trying to find where that quadratic hits that line. So -2, 0 is an x-intercept. And now, second enter, we're going to override just this -2 and that -2 with a -1. So make sure you don't accidentally change that -2. And that gives us -2. Now remember, we should get -2 and 0 for those other points, but we don't want to assume. We want to explicitly plug in one of those. So second enter, I'm going to override the 1 with a 0, and then use the delete key, which is right next to my arrows, to get rid of the negative. So then over here, override the 1 with a 0, delete the negative. And we get -2. There's that repeated range value that we love so much. So that means that would have to be 0 as well. So let's see what we have so far. There's -2, 0, -1, -2. The vertex, 0, -2, and 1, 0. Now, as you can see, we are really close to that line there, but is that an exact point? And folks, except for a few of the solve algebraically ones, these should all be exact, easy to find points. So I have not found the intersection point yet, so we're going to keep going. We're going to try plugging in -3 and +2, so going left and right. Now, looking at what I already have on my calculator, which value is going to be easier to plug in, -3 or 2? 2, I don't want to have to import that negative sign. So let's do 2 and 2, and we get 4. So -3, 4, and 2, 4. So -3, 4, boop, and 2, 4. Ooh, hooray! So that is exactly where that quadratic is hitting that line. Now, is it going to hit this other point as well? I don't know. Maybe we should go 1 point further just to be sure. But just note, we did find an intersection point here. So let's go 1 point further and just see what my graph does to the right of that point. So I'm going to plug in 3. And we get 10. So 10 for the 3 and 10 for the -4. So 3, 10 is up here. And -4, 10 is up there. So folks, as I swoosh through these to draw my quadratic, how many solutions do we have? Only that one. So it is only at that point the line is touching. Yeah, it's really, really, really close everywhere around it. But as we can see, the quadratic curves into the line and hits it once, and then it starts to curve back out away from it. So one solution for this one at 2, 4. Go ahead and put a box around it. 2, 4. One solution. Folks, what questions do we have on that process so far? Graphing the lines, graphing the quadratic, and finding where they intersect. Example 2. I want you to put some big old stars around this one, because this actually caused quite a few issues on that last test that we took. this negative out in front of the x squared. And if you check back in your Unit 4 Part 1 notes, you'll see that we had started there as well. So that negative, when I plug in values, whether positive or negative, it is always going to go on the outside of the parentheses. So we'll go ahead and label this number 1, equation number 1, and this equation number 2. So what is equation number 1? It's a quadratic. We've got ax squared plus bx plus c. Q for quadratic. And then this one, equation number 2, is a line. Now, this one is in standard form. We'll review the cover-up method next week when we start studying for term tests. This one is easy enough to simply subtract that 2x over to the other side to put it in slope-intercept form. And the reason why we want to rely or lean on slope-intercept form a little bit more on this is because slope-intercept form allows me to generate exact points as we count up using the slope, whereas with standard form, it's like, we got 2 points. Best I can do is 2 points. So slope-intercept form, we can generate more along the line. Standard form, all we can do is the x and the y-intercept. So folks, let's go ahead and graph that line. We've got a y-intercept of 5, boink, right there on the y-axis. And our slope is negative 2. So negative leading coefficient, are we going to do this or are we going to do this? This. Leading coefficient is negative, means the right arrow goes down. Yes, those same rules apply for lines as well as some of those more complicated polynomials we did. So we're going to go down 2, forward 1, down 2, forward, down 2, forward 1. And I'm going to fill out the expanse of this graph. Seems like a lot, Mrs. Cairo. It is, and we're actually going to go up 2, back 1, up 2, back 1. We want as many exact points as possible, especially with you guys not using rulers, so that we can tell exactly where that quadratic is hitting. So we're going to label this line number 2. All right, folks, so there's our line. Next, it's time for the quadratic. We start with our axis of symmetry. Negative b, negative 2, over 2 times the a value of negative 1. So I get negative 2 over negative 2. And my axis of symmetry is x equals 1. So I'm going to go ahead and draw in that line at x equals 1. What do we know about the vertex then? It has to have an x value of 1. So I'm not going to explicitly write the vertex like I did over here. Instead, I'm just going to go straight to making this table obnoxiously large like we did the last one. And I'm just going to center my vertex in the middle. So we know that the vertex x value has to be 1. But now we need to find the corresponding y value that goes with it. Ooh, that glare is awful. All right, folks, so we need to plug 1 in to this equation. So that negative, is it getting squared? No, just like if I had negative 5x squared, that negative is its own thing. It's a coefficient in front of the x. So when I put that 1 in as an input, I'm really doing this. The negative goes on the outside, the 1 goes in parentheses. Then we're, oops, not double squared. We're going to square once, and then plus 2 times 1 plus 2. And we get 3 for our vertex x value. And we plot that, and, well, hallelujah, there is one of our intersection points right on the vertex. So automatically, we have one solution. Now, we might have one solution only. We might have two solutions. But to graph that parabola, we need at least 5 points. So let's go 0 and -1, down 2 values, and up 2 values. And folks, normally we start at the top, but since I've already got positive numbers plugged in here, I'm not even going to mess around with those negatives. I'm going to go straight to replacing the 1 with a 2 to get 2 for that output. And then replace these 2's with a 3 to get -1. And now I can plug in 0. And that gives me 2. And once we have verified those repeated values around the vertex, then I can assume that that is -1 as well. So let's see what that does for us as far as this quadratic goes. We've got -1, -1, 0, 2, 2, 2. Oh, it's a sand graph. And then 3, -1. Behold, another solution. So that's why I like to do the line first and then the quadratic, because as soon as I see it hitting a second time, I know it's not going to hit a third time, and we can go ahead and stop with our points. So for this one, we have two solutions, 1 and 3, and 3, and -1. So two solutions. Now, what is special about these two solutions, and any solution to a system, is it should work with equations. So I could plug this in for x and y in the first equation, x and y in the second equation, and we would get true statements for both equations and for both of those points. Folks, let's go ahead and take a quick breather before we move on to page 2.